We're back for part 2 here, which is the lesson. Here are the things that you were supposed to find out or learn or remember, I hope, working on that investigation. The commutative property of vector addition is that when we add two vectors, it doesn't matter the order of them, right? And that idea was easy to see. If we had two vectors u and v, that's exactly the same. Now I'm not going to get to do that, so let's copy v here. Well, that's not quite v, but you get the idea. That if I went v first and then u, the resultant, the answer vector, is the same. Remember, position doesn't matter. That vector is the same, isn't it? This is the same thing. U plus v is the same thing as v plus u, and in fact, we kind of called that the parallelogram property, didn't we? That when we put these together, that it makes a parallelogram, and in the middle of it is the resultant, and it doesn't matter the order. The associative property of vector addition is that if I go u plus v and got an answer, and then took that and added a third vector w, that would be the exact same thing as if I did v and w first and got an answer, and then added u to it. Okay? And hopefully you came up with a decent diagram with that. I think the book's got pretty good illustrations of this as well. I won't try and step you through that. If you want to ask about how a picture would show these things, be sure to ask in class. The distributive property of scalars over vector addition is this. When I have a scalar times the sum of two vectors, which is just another vector, that it's the same as the scalar times the vector plus the scalar times the other vector, and then I add those vectors up as well. Exactly what you would think, by the way. In real numbers, for instance, the associative property, does it matter if we go 2 plus 3 first and get 5 plus 5 is 10, or is it okay for us to go 3 plus 5 first and get 8 and then get 10? Yeah, okay, well, that's the same thing for vectors. And here, a common one that we think of is this is the distributive property for algebra. Back in grade 9, we realized to remove brackets like this, we can just distribute the 2 over the adding or subtracting here, and that works for vectors as well. And in fact, most of these things are going to feel very familiar from what we know about dealing with polynomials. So associative law of scalar multiplication, this is the one that I actually illustrated when I was setting up the activity. So if I have a scalar times a vector and then a scalar times that new vector, I could multiply the scalars first and basically collect up the number parts and write it out front. And there's, I illustrated that one. Distributive property of vectors over scalar addition. So scalar addition, can I do this? If I have two numbers added times a vector, is this the same thing as this? And indeed it is. Indeed it is. It's almost, we could almost think of this as collecting like vectors, right? If we had 2x plus 5x in grade 9 or grade 8, we'd go, okay, yeah, 2 plus 5 is 7x. Yeah, I can collect like terms. And this is true if this were a vector. Okay? So 2 times a vector plus 5 times a vector is indeed 7 times a vector. And that's kind of like the example that we're going to get to here shortly. First example is actually pretty easy. Simplify this. It kind of feels like algebra. It feels like polynomials. So generally, if you think that, if it feels like you should be able to do something, yeah, you can. You can. And why? It's because all of these properties hold true. So for instance, the first thing that I'd be tempted to do is distribute this. And I'm going to go slow here because which property is that? That's this property, right? So a scalar times the sum of two vectors or three vectors, I can distribute the scalar. Okay, well, let's distribute the scalar. And I'm going slow. I know that when you get into your homework, you're going to go a little bit faster than this, and that'll be fine. Where A, B, and C are some old vector, we don't care what. I'm going to distribute the -1 through. Say, Mr. Resto, can we skip a step? You're going too slow. Well, hang on. This is our first example like this, right? So, well, why didn't you make that 12 straight off? Well, it's because that's a whole separate rule. That's this rule, right? If I have 4 times 3, that's the same as 4 times 3 in brackets. That is the same as 12. Oops, went the wrong way. So this is 12a and 4b, and I'm using that, collecting up the scalar's ID. Okay, fine. So I can do that. Yes, you can do that. Now, notice that could I put this one and this one together? Well, yeah, you can because of this property, right? I can shuffle them back and forth so they're together. So I could, shuffle these two, then this one shuffles over here, and I could put these two close together. Do you have to show this step? Well, for this example, you have to show this step. And then this one shuffles over here, so it's with its like term. And then I can distribute the scalar for the scalar multiple of that vector. So this sort of thing. Well, why can I do that? That's because of this rule. That's that last rule, right? Where I was just talking about that. And so what's the final answer? Well, it's exactly and feels exactly like we thought it should. It feels like algebra. So do you have to show all these steps? No. No, don't show all these steps, but I wanted to break it down. It was our first algebra of vectors sort of thing, so I wanted to make sure we understood that that was what we were doing. All right, what do we got? If blah, 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 determine x plus 2y minus z in terms of I, j, and k. So what do I want? I want to determine this, so I'm going to write down that. But I'm going to do a bunch of work, and I should have only i's, j's, and k's. And what's all this i's, j's, and k's business? Well, we're not too worried about that yet, but it's going to be important soon. So what's this x? Well, x is this expression, so I'm going to put that in there. Do I have to put the little arrows up above? Absolutely you have to, because it's a vector. Plus 2 times y, which is that expression, goes in here, minus z. Okay, dandy. And now I'm going to treat it like algebra. Okay, I'm going to, remove the brackets by distributing the scalars where I need to, and then collect some like terms, and it's easy peasy. And so here, even though the last time I went 2 bracket -4, I'm actually just going to use 2 vector rules in one, and I'm going to do the same thing here. You can scream at me if I'm making an arithmetic error. I might hear you through the video, I don't know. And then again, I can shuffle them all together and use the scalar distribution. But really what I'm doing is I'm collecting like vectors. Right, there we go. And that one is like that one. That makes minus 2j. And then 1 and like there. Oh, I missed that one. I missed that j. Whoops. So hang on. What's negative 2j plus j? Negative 2j plus j is 0j, or the 0 vector. I could just leave that out, right? This is just the 0 vector, which is gone, just like it would be in polynomials. So that behaves in the same way too. There's a k, and here's a k, and here's a k. Let's make sure I don't miss one this time. That's 1 minus 8 is minus 7 minus 12k, and there's my final answer, assuming I never made, or did I make an arithmetic error? No, I'm okay. Yeah. Minus 12k. Dandy. One more example, and this is a doozy. So if A is equal to that and B is equal to that, find X and Y in terms of A and B. So find X and Y in terms of A and B. So this is what we want. Here's the goal. X equals something A plus something else B, and Y equals blah A plus something else B, where these are some scalars, right? Essentially, we need to turn these two expressions inside out. What we want to do is from one of them eliminate the x's, and from the other one eliminate the y's. That's what we're going to do. So watch the magic here. I'm going to write down this one. So A equals 5x minus 4y, and I'm going to go, this is just the first one, and then I'm going to go 2 times the second one, and I'll show you, whoops, that's B. And I'll show you why in a second. Bear with me. So that's 6x and plus 4y. See, now what I'm going to do, because of this, and this will feel familiar, this should feel like 2 equations, 2 unknowns. This is essentially elimination. I'm going to eliminate the y from this set of equations. On the right-hand side, I'm going to have 5x and 6x, which is 11x. On the left-hand side, I have my expression. No y. Suddenly, it's looking like that, isn't it? Right? I get a little smiley face. This idea of eliminating the y's is going to allow me to write it like this. And so now if I divide by 11 on each side, on each piece, divide by 11, then therefore x is equal to 1/11 A plus 2/11 B. And there's my expression for x. Well, how do I get one for y? Well, I pull the same trick, the exact same trick, but I'm going to eliminate the x's. So how do I eliminate the x's here? Well, they don't line up as nice as the y's. I'm going to need to multiply this one by 3. I'm going to multiply this one by 5 and subtract. Now, actually, I'm not going to do that because I don't like subtracting, but that's another story. I'll get to that in a second. So I'm going to multiply this one by 3. I'm going to go 3 times 1, which is 3a, 15x minus 12y. And over here, I'm going to multiply this one. I told you I don't like subtracting, so I'm going to multiply by negative 5. Negative 5b equals negative 15x and negative 10y. And now notice that because I multiplied by a negative, then I can just add. You see, when I add, the x's are gone. Minus 22y, divide by the minus 22 on each of the pieces, and I get y equals negative 3/22 over a. This skill is important, and we'll see why very shortly. But essentially what we had is we had a in terms of 2 vectors x and y, and then we turned it around, and essentially we changed the subject. We changed it from inputs to outputs, and this is an important skill later in the chapter. Okay, pretty neat example. There's one piece, and there's my other piece. That's my solution. Bing, done. By the way, if you need some extra questions, or you have some time to do some extra review, that mid-chapter review is awesome. But there's today's homework right there.